The objective of this video is to express the general expression for an ACF in an AR2 model using roots of the characteristic polynomial. So we know the AR2 model is given by xt minus 1 minus phi 2 xt minus 2 equals a sub t. This would imply xt minus phi 1 b1, b, xt minus phi 2 b squared, xt equals at, and xt times 1 minus phi 1b minus phi 2b squared equals a sub t. This would mean the characteristic polynomial is phi of b equal to 1 minus phi 1b minus phi 2b squared. We could write it in terms of a different variable rather than the backwards operator. So perhaps we could call it phi of s is equal to 1 minus phi 1s minus phi 2s squared. So that is a polynomial function. So we know that polynomial functions can be expressed in terms of products, and we're going to have roots always, so they might be complex real, repeated real, so we could always represent the polynomial as a product of factors. If we recall, for AR1, phi of s is 1 minus phi 1 times s. This would mean the root of the polynomial, which is s equal to 1 over phi 1, or phi 1 equals 1 over s, which is s inverse. So in a simplistic sense, we can get the idea that the coefficient is related to the inverse of the root. But what we have to know about AR2 is that it is not as straightforward, in the sense phi 1 is not equal to 1 over the first root, and phi 2 is not equal to 1 over the second root. Rather, they are functions of the inverses of the roots. So how do we get that far? So suppose the factored form of phi of s be 1 minus r1 inverse times s minus r2 inverse times s, where r1 and r2 are the roots of the characteristic polynomial. So if we don't want all the negative signs, we could also write it as alpha 1 equals r1 inverse and alpha 2 equals r2 inverse. This would mean phi of s, which is equal to 1 minus phi 1s minus phi 2s squared, can be expressed as 1 minus r1 inverse s times 1 minus r2 inverse s, which would equal to 1 minus alpha 1 times s multiplied by 1 minus alpha 2 times s. So that right here is the original polynomial, and that is the factored form. So we can rewrite 1 minus phi1s minus phi2s squared equals 1 minus alpha 1s times 1 minus alpha 2s. So if I FOIL, we'd get 1 minus alpha 2s minus alpha 1s plus alpha 1 alpha 2 times s. So 1 minus phi1s minus phi2 s squared would equal to 1 minus alpha 1 plus alpha 2 times s plus alpha 1 alpha 2 times s. Now by direct comparison, we can see that phi1 is equal to alpha 1 plus alpha 2, and phi2 is equal to negative alpha 1 alpha 2. So that's it. We can move on to the general form of the ACF, or the general solution, or the general expression. Which is C1 alpha 1 raised negative k plus C2 alpha 2 raised negative k. Now we want to solve for C1 and C2. So we have to make use of the row 1 and row 2 that we know in the Yule-Walker equations to find C1 and C2, so that we can generalize the entire ACF. So if we recall the Yule-Walker equations, row 1 equals phi1 plus row 1 phi2, and row 2 is equal to phi1 row 1 plus phi2. So that would imply row 1 minus row 1 phi2 equals phi1, which would simply mean row 1 is phi1 over 1 minus phi2. We can take that value, plug it in the second equation. We will get row 1 times phi1 times phi1 over 1 minus phi2 plus phi2, which would be phi1 squared over 1 minus phi2 plus phi2, and that would be equal to phi1 squared plus phi2 minus phi2 squared over 1 minus phi2. All I did is find the common denominator and combine the two terms. Now I'm going to rewrite row 1 and row 2 in terms of alpha 1 and alpha 2. So what we have is row 1 equals, we know phi1 is alpha 1 plus alpha 2, and we also know that phi2 is negative alpha 1 alpha 2, so negative alpha 1 alpha 2, we get alpha 1 plus alpha 2 over 1 plus alpha 1 alpha 2. In a similar manner, row 2 is phi1 squared plus phi2 minus phi2 squared over 1 minus phi 2. Phi 1 squared is alpha 1 plus alpha 2 squared. Phi 2 is negative alpha 1 alpha 2 negative alpha 1 alpha 2 squared for phi 2 divided by 1 minus alpha 1 alpha 2. And that would equal to alpha 1 squared plus alpha 2 squared plus 2 alpha 1 alpha 2 minus alpha 1 alpha 2 minus alpha 1 squared alpha 2 squared divided by 1 plus alpha 1 alpha 2. So we could cancel a couple of terms. We'd end up having alpha 1 squared plus alpha 2 squared plus alpha 1 alpha 2 minus alpha 1 squared alpha 2 squared over 1 plus alpha 1 alpha 2. We can now go back to the general expression for row k and plug in k equals 1 and k equals 2. So when k is equal to 1, row 1 would equal C1 alpha 1 raised negative 1 plus C2 alpha 2 raised negative 1. Sorry, it should actually be positive, because if you recall, the general expression has the root raised to the power of negative k. So we have represented alpha 1 as the negative of the root. So this expression should only contain positive k's right here and right there. So what we will have here is alpha 1 plus alpha 2 raised 1, and row 2 would equal to C1 alpha 1 squared plus C2 alpha 2 squared. So the reason for that is row k is C1 the root raised negative k plus C2 the second root raised negative k. What we have done here is rewritten. We have it rewritten as C2 times R2 inverse raised k, and we called the roots as, or the inverse roots as alpha 1, so we would get C2 alpha 2 raised k, and which is why the exponent in the general expression now becomes positive. So we have two equations, and now we have C1 alpha 1 plus C2 alpha 2 equals row 1, C1 alpha 1 squared plus C2 alpha 2 squared equals row 2. But we have found the expression for row 1 in terms of alpha 1 and alpha 2, which is alpha 1 plus alpha 2 divided by 1 plus alpha 1 alpha 2. Likewise, row 2 is alpha 1 squared plus alpha 2 squared plus alpha 1 alpha 2 minus alpha 1 squared alpha 2 squared divided by 1 plus alpha 1 alpha 2. So we want to solve the system of equations, so what I'm going to do is multiply the first equation by alpha 1. So I would get alpha 1 squared plus alpha 1 alpha 2 over 1 plus alpha 1 alpha 2. And C1 alpha 1 squared plus C2 alpha 2 squared would be the second equation. Alpha 1 squared plus alpha 2 squared plus alpha 1 alpha 2 minus alpha 1 squared alpha 2 squared over 1 plus alpha 1 alpha 2. So when we subtract, those two terms would go away. So we will have C2 times alpha 1 alpha 2 minus alpha 2 squared. That would equal to alpha 1 squared plus alpha 1 alpha 2 minus alpha 1 squared minus alpha 2 squared minus alpha 1 alpha 2 plus alpha 1 squared alpha 2 squared. So those two terms would go away, those two terms would go away, leaving us with C2 times alpha 1 alpha 2 minus alpha 2 squared equals alpha 1 squared alpha 2 squared minus alpha 2 squared divided by 1 plus alpha 1 alpha 2. We have an alpha 2 in common, so alpha 1 minus alpha 2 times alpha 2. I'm going to pull a negative alpha 2 out, or negative alpha 2 squared, which would mean 1 minus alpha 1 squared over 1 plus alpha 1 alpha 2. The alpha 2's would get cancelled, so the constant C2 is simply negative alpha 2 times 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So now that we have the value of C2, we're going to take the value of C2, plug it in one of the two equations and solve for C1. So we know C1 alpha 1 plus C2 alpha 2 equals rho 1, which is simply alpha 1 plus alpha 2 over 1 plus alpha 1 alpha 2. So we're going to plug in C2, which is negative alpha 2 times 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2 multiplied by alpha 2, which would equal to alpha 1 plus alpha 2 divided by 1 plus alpha 1 alpha 2. So C1 alpha 1 minus alpha 2 squared multiplied by 1 minus alpha 1 squared over alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2 equals alpha 1 plus alpha 2 divided by 1 plus alpha 1 alpha 2. We move that huge term on the left-hand side to the right-hand side, so we have alpha 1 plus alpha 2 over 1 plus alpha 1 alpha 2 plus alpha 2 squared times 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. When we take the common denominator, we'd end up having alpha 1 plus alpha 2 times alpha 1 minus alpha 2 divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2 plus alpha 2 squared multiplied by 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So this would mean C1 alpha 1 equals alpha 1 squared minus alpha 2 squared plus alpha 2 squared times 1 minus alpha 1 squared, and the entire thing divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2, which would give us alpha 1 squared minus alpha 2 squared plus alpha 2 squared minus alpha 1 squared, alpha 2 squared, divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. The alpha 2 squareds will go away, and we will have alpha 1 squared minus alpha 1 squared times alpha 2 squared over alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2, which would equal to alpha 1 squared times 1 minus alpha 2 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. Mind you that that is equal to C1 alpha 1. So if we divide by alpha 1, we'd have C1 equals alpha 1 times 1 minus alpha 2 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So now we go back to the original expression, which is the general expression for row K. Is row K equal to C1 alpha 1 raised K plus C2 alpha 2 raised K. C1 is alpha 1 times 1 minus alpha 2 squared over alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2 times alpha 1 raised K. And C2 is negative alpha 2 times 1 minus alpha 1 squared divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2 multiplied by alpha 2 raised K. So row K would now equal to alpha 1 raised K plus 1 times 1 minus alpha 1 squared over alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2, and over here minus alpha 2 raised K plus 1 minus alpha 1 squared over alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2, which would simply mean row K is equal to alpha 1 raised K plus 1 minus alpha 1 squared minus alpha 2 raised K plus 1 times 1 minus alpha 1 squared. Excuse me, the first term here has to be alpha 2 divided by alpha 1 minus alpha 2 times 1 plus alpha 1 alpha 2. So that is the general expression for row K, and notice the above expression doesn't have C1 and C2 because we already solved for C1 and C2, and it only depends on the roots of the characteristic polynomial phi of S, which are R1 and R2. So in our notation, we used alpha 1 as R1 inverse and alpha 2 as R2 inverse. So what is the benefit of this expression? In the past, when we connected the roots of the characteristic polynomial to the general expression of the ACF, we had to solve for the constants C1 and C2 by inverting the matrix. With this expression, we don't even have to invert the matrix to find the constants. We can simply find the roots of the characteristic polynomial, plug it in this equation, and get the general expression for the ACF. Mind you that this particular expression works only for an AR2 model and not for any other AR models.